Alright everyone, for today's physics problem, I'm doing number 29.19, and this one says a 2 centimeter by 2 centimeter parallel plate capacitor has a 2 millimeter spacing in between it, and the electric field strength inside the capacitor is 10 times 10 to the 5th volts per meter. Alright, just drawing this out to get a little visual. Here we go, we got our parallel plate capacitor right here. Positives up here, negatives down here. In between them we got 2 millimeters, and if we remember, they're 2 centimeter by 2 centimeter. No centimeter. Whoop. All right, and we also know that the electric field is 10 times 10 to the 5th volts per meter. So for part A, I'll do it down here. A is asking, what is the potential difference across the capacitor? Alright, so we know that E equals delta V over delta D. So now we just want to solve for the potential difference across it. So multiplying delta D on each side, we get delta D times E equals delta V. Now it goes in a distance, or the delta D is 2.0 millimeters, so we got to convert that to meters. That's 0.002 meters times the E, which is 10 times 10 to the 5th volts per meter, and that equals delta V. Sorry, I got my hand out of the way. And we now know that delta V is, what is that? That is 2,000 volts. Now part B is asking how much charge is on each plate. So this is a little blast from the past, because it's dealing with the charge on each plate. So we know that for a parallel plate capacitor from earlier chapters or from an earlier video, that we found out that the electric field E equals sigma over epsilon naught. Alright, now we can also substitute right here that sigma equals the charge over the area, because we're giving the area earlier in the problem, the 2 centimeter by 2 centimeter right here. So plugging that in, we get E equals Q over A over epsilon naught. Now isolating Q, because we want to find the charge on each plate, we get Q equals epsilon naught times E times the area. Now plugging those in for real numbers, we get Q equals epsilon naught, and that is 8.85 times 10 to the negative 12 coulomb squared per newton meter squared. The E, which is what is that, 10 times 10 to the 5th volts per meter, and the A, which was centimeters, 2 by 2 centimeter. So we gotta convert that to meters, which is 0.02 meters squared. Alright, and this all comes out to as Q equals 3.5 times 10 to negative 11 coulombs. So if you're looking at these answers right here, these two, and comparing them to what the answer key says, you notice that they're all off by 10. And I noticed that too, which kind of freaked me out at first. But then I realized that the book wrote the E as 10 times 10 to the 5th volts per meter. Now this isn't actually in scientific notation. That should be 1.0 times 10 to the 6th volts per meter. Now I think what the book meant to write was 1.0 times 10 to the 5th volts per meter, which would give you the answers in the answer key that's posted online, which is really 3.5 times 10 to the negative 10th, I think 200 volts. So this would give you those answers, but that's not what the E value is. The E value is 10 times 10 to the 5th, so that's just something to consider as you're doing this problem. Alright, thank you.